Hi there. This is lecture 3, which will be about section 6.4, which is work, and 6.5 in the text, which is about the average value of a function. So let's get started. We're skipping 6.3, by the way, which is a different way to do volumes. This 6.3 is an optional section, which I don't cover usually. Okay, here we go. Okay, so what is 6.4 about? I said it's about work. The basic idea is this. What is the work done in, say, pulling, here's a concrete thing, pulling an object across the floor? You can think about how much force you've expended over the distance of pulling that object along the floor. So it would be force times distance. But that's provided that the force is constant. Okay, so what if the force is not constant? So let's depict that in the following poorly drawn picture, which I will erase now, and I'll start over. So we have a set of axes, and the horizontal is indicated by the x-axis, and suppose we are dragging something from point A to point B, but there's a variable force at every moment along the horizontal. You might have a different force value. So let's assume maybe it's a graph like this. So this is the force. So it's given by, say, a function of x, where x is lying between A and B. Okay, so here's how we can try to understand what work is when the force is variable. We take a little strip between, say, a point which I'll call xi and xi plus 1, and delta x is xi plus 1 minus xi. And if this strip is thin enough, then the work done along this curve, the work done of the force, we can pretend the force is roughly constant on this thin interval xi to xi plus 1. So we can think of the work done along the strip, the work from xi to xi plus 1 as being approximately given by, well, the value of the force, say, at xi, times the distance you travel from xi to xi plus 1, which we said was delta x. This is only approximate because the force is changing from along xi to xi plus 1, but if that delta x is small, this is a fairly good approximation. Okay, and now if we want to get an approximation of the total work done from A to B, x equals A to x equals B, that's going to be the sum over all the strips you're going to be taking. So that would be the sum. I goes from 1 to I equals n of f of xi times delta x. Well, that's just a Riemann sum. And so what we're going to take delta x going to 0, which means n is going to infinity. The number of points we take between A and B gets large, and that becomes a definite integral from A to B of f of x dx. So that's the work, and that's going to not be an approximation anymore. It's going to be an equality. And here we're assuming the force is a continuous. So let's assume f of x is continuous on AB, so the definite integral is actually defined. Okay, Before I move to doing problems, it makes sense to talk about units. Now, there are two kinds of units. There are the English system units, which are easier to remember. It's work has the units of foot, the dimensions of foot times pounds. So we give it the unit foot pounds. Now, in the international system, also known as the metric system, it's given in joules, J, and a joule, that's a more complicated unit for me. It's given by newtons, Newton meters in notation Nm, and that would be, and a newton is a kilogram meter per second squared times, and then the meter portion gives you an extra meter, so it would be kilogram meters per second squared. S is second. Okay, so those are the two units that are used in all the problems. And if you don't have like meters, you're working with centimeters, you're going to have to convert to meters, of course, in order to get it in terms of joules eventually. Okay, so now what I'm going to do is I'm going to do a problem from the text. Let me pause for a moment and pull up the text. So I'm going to be doing problem number 3, which is a variable force of 5x to the minus 2. This is problem number 3 on page 470 in the exercises of 6.4. A variable force of 5x to the minus 2 pounds moves an object along a straight line when it is x feet from the origin. Calculate the work done in moving the object from 1 foot to 10 feet. Okay, so what I'm going to do is go back to the whiteboard, clear the screen, and work on this problem here. So what do we got? We got F. This is number 6.4, problem 6.4, number 3 on page 470. It's an exercise, and the force was given to us as f of x equals 5x to the minus 2, which I'd prefer to write as 5 over x squared. And x was going from 1 to 10, so 1 to 10. So you're looking at a curve which is decreasing. That's what it's doing. So 1 is less than or equal to x is less than or equal to 10. And the work will be given by the integral from 1 to 10 of 5 over x squared dx, which is given by negative 5 over x. The antiderivative of 5 over x squared is negative 5 over x from x equals 1 to x equals 10. And so you're going to get negative 5/10 minus negative 1/10, which becomes uh, negative 5. Sorry, that was bad. It's not negative 1/10. It turns out to be negative 5 over 1, which gives me 5 minus 1/2, which is 4.5 foot-pounds. And that is the answer, 4.5 foot-pounds. Okay, so there's another kind of problem I want to cover in this business of work, which are spring problems. So there's something called Hooke's law. And it goes like this. You have a spring, maybe it's tethered to a wall. Here's indicating the spring, and then the end of the spring is maybe a weight or something. Not necessarily. And this is in the rest position, we'll put the origin here. This is the origin. This is the rest position. And we pull, this is just the handle of the spring, so not really a weight. And we're going to pull, we're going to stretch the string. We stretch it by a certain length, maybe stretch it x units outward from rests. So we stretch it out to here. So we pull the spring out by x units. And then Hooke's law, which is something that was discovered by experiment, is that if x is not large, then the force f of x is the force of stretching the spring x units is proportional to x. So it's k times x, where x is the displacement, I said, and k is a constant, which is called the spring constant. And it depends upon what the spring is made of and other things. It's different for different springs. Okay, so that is Hooke's law, and we're going to solve a problem with Hooke's law. So here is an example. We're given a spring, and with a natural length, that's a rest length of 1 meter. So we're given a spring, and then we apply a force of 25 newtons, and it stretches the spring by a quarter of a meter, by 0.25 meters. So the question is compute the work done, and there are two parts of this problem. When the spring is stretched, uh, 2 meters beyond its natural length, and then in part B, when the spring is stretched from 1.5 meters to 1.5 to say 2.5 meters. Okay, so that's these are two different problems, obviously. So let me solve both problems in this little box. So solution of A is, well, we first have to compute the spring constant. So how do we do that? Well, we're given something. We know that 25 Newton forces will stretch the spring a quarter of a meter. So that tells me that 25 newtons are given by the spring constant times 0.25 meters. Okay, so let me, I goofed on that. Got to erase. So 0.25 meters. So we can solve for K by dividing both sides by 2.25. So K is 25. I'm leaving the units in newtons over 0.25 meters. And that gives me, I guess, 100. And I'm going to, if you take newtons and divide by meters, you'll get, I guess, kilogram meters per second squared. So that's what K is. K is 100. Okay, so that tells me f of x equals, which is kx, is 100x. Okay, so now that tells me the work done in moving the string, when the spring is stretched from its natural length to 2 meters, is the integral from 0 to 2 of 100x dx. and we get 50x squared when we take the antiderivative. We're evaluating it from 0 to 2. And then we get, what do we get? We get 50 times 2 squared, which is 4. So it's 200. It looks like 200, and now the units are joules in this case. So that's part A. Let's go to part B. I'll do that below. So we're going in part B, it's similar. You're integrating 100x dx, but now we're going from 1.5 meters to 2.5 meters. We have to think about what that means. It's 1.5 meters beyond the natural length of 1 meter, right? So that means it's been displaced initially by 0.5 meters. And then in the 2.5 meter case, it's being displaced 2.5 minus 1, which is 1.5 meters. So we get 50x squared evaluated from 0.5 to 1.5, which is 50x squared times, let me think of 1.5 as 3 halves. So 3 halves squared minus 50 times 1 half squared, which is 50. I'll factor out of 50. We get 9 quarters minus 1 quarter. So that's 50 times 8 quarters of 50 times 2, which is 100 joules. So that's the solution to part B. Okay, very good. So we've solved our first problem here, first non-trivial problem with work. When I say non-trivial, I mean not completely obvious what to do from just the way the problem is stated. Okay, so the next problem I want to do is an example in the book, not an exercise, but an example. And it's going to be, let me clear the screen. So it's going to be the example number 4 on page 469. And I'm only going to do part A, just because that sort of has the key idea. And let me try to pull up the text to do this. Okay, so where is that? That's over right here. So it is this is a cable problem, example 4. It says a 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. And part A, which is what I'm going to do, is how much work is required to lift the cable to the top of the building. So there's a picture given to us, and I'm going to follow this picture. The building is represented by this drawing, and I'm going to explain. I'm going to give the same, more or less the same explanation as done in the book. Okay, so how does it go? So let me draw a picture. So we have a 200-pound cable. Oops, that's not how you spell cable. And it's 100 feet long. And it's sitting off the top. It's lying off the top of a building. So the distance the cable is 100 feet total. Now, we can figure out the weight per foot. The weight per foot is 200 over 100, so it's 2 pounds per foot. Okay, that's important for the problem because that so now we want to figure out the work in lifting the cable all the way to the top. Okay, so the idea is to put the origin at the top. Okay, and what we're going to do is let me draw the picture. I'm going to rotate the picture 90 degrees. So suppose this is a little section of cable going from xi to xi plus 1. So xi plus 1. Okay, and the width is delta x. So delta x is this little distance here. Okay, and the question I want to so the first of all, what is the weight of the section of cable we're discussing, the relevant section of cable? Well, it's given by 2 pounds per foot, and if it's delta x feet, it's going to be 2 delta x. That's the weight of that little section of cable, and that's in pounds, of course. Okay, so what's the total work done on the moving the ith part of the cable all the way, moving the ith part of the cable? Well, this distance to xi, the distance is given by xi, right? So the work done in moving the ith section of cable, this little piece of cable all the way to the top it's not exact because the force is not constant along that section of cable. It's 2 delta x times xi. So now, if we do move every section of cable, so the total work, you get the total work approximately. That's given by the sum over I going from 1 to n, say there are n sections of 2xi. I'll put the delta x at the end. So this is a Riemann sum, and then we take delta x going to 0, in other words, n going to infinity, to get an exact answer. The total work, W, is given by the integral from 0 to 100, obviously, 2x dx. The 2xi becomes 2x, and the delta x becomes dx. Okay, so this is all set up correctly now, and the rest of it is easy. It's x squared evaluated from 0 to 100, and 100 squared is 10,000 foot-pounds, and that's the answer to this question. Okay. So now we move on. We're done with work, and now we move on to the next topic, which I guess is section 6.5. Let me clear the screen. And 6.5 is the average value of a function. Okay, so here's some motivation. Suppose we were to take continuous temperature readings of your room, or where you're sitting in your room, say from 6 a.m. to 6 p.m. So, probably, so here's the temperature T. Then you're going to get like a curve. The temperature is going to go up, and probably around noon, it's going to peak, and then it's going to go down as the sun goes down. Okay, so let's say it looks like this, the curve. So the question is, what's the average of the temperature over time? Well, you can do this with any function. So let f of x be any function. So not necessarily temperature, okay? And then we could ask what's the average of a function, the average value of a function. So one way to do this is to start choosing points along the axis. Let me start with a new graph here. So rather than do it working here, I'm gonna put in a new graph. So let's draw a new graph. So here's the x-axis, here's the y-axis, here's A, and here's B, and here's a function, f of x. So now suppose we cut up the interval into subintervals, etc. So we have the ith point, and then we have the I plus first point, and we look at all the values at these subdivision points. So here's an estimated average value, estimated average. we take the values along this curve of f of x1 plus f of x2, etc., and divide by n. That's how you average like exam grades, for example, right? Now, what is n? Well, n is the number of subintervals. So n, b minus a over n is delta x. So in other words, delta x over b minus a is equal to n. 1 over n. So this estimated average is given by so 1 over n, it's given by f of x1 plus all the way up to f of xn times 1 over n. But 1 over n is, we saw, given by delta x over b minus a. Now we can rewrite this as the sum. I need more room, so I'm going to erase this equal sign. It's 1 over b minus a of f of xi times delta x. I goes from 1 to n. So that's the estimated average. Now what I'm going to do is let delta x go to 0. So we're going to take delta x to 0 and n going to infinity. That happens at the same time. And what happens is that this Riemann sum with this 1 over b minus a in front of it becomes 1 over b minus a times the integral from a to b of f of x dx. And this is called the average value of the function f. Okay, so that's pretty simple. And I'm going to just do 2 elementary examples of the average value of a function. So let me erase most of what's here. I'll just leave the formula in the box. Erasing by hand takes much longer than clearing the screen. Okay, so here's an example. Let's take f of x equals x squared, and where we're on the interval 1, 2. What's the average value of f of x equals x squared on the interval from 1 to 2? So this is what the function looks like. It's part of a parabola. So it's going to be f average is the integral of x squared dx times 1 over 2 minus 1. And the integral is from 1 to 2. And so it's 1 over 2 minus 1 is 1, x cubed over 3 from 1 to 2, which is 8/3 minus 1/3, which is 7/3. Here's another example. F of x is ln of x over x on the interval 1, 5. So what do we get? So f average is given by 1 over 5 minus 1, the integral from 1 to 5 of ln of x over x dx. So, and this is 1 over 4, integral from 1 to 5 ln of x over x dx. Now, how do we compute this integral ln of x over x dx? We do it by substitution. So that means, and the substitution I'm going to use is u equals ln of x. So du is then dx over x. Right, the derivative ln of x is 1 over x. And so this integral on the right side of the screen is 1/4. Now we have to figure out the new limits of integration. Now when x is 1, u is ln of 1. ln of 1 is 0. And when x is 5, we get ln of 5. And so then we have ln of x is u, and then we have dx over x remaining, that's du. So it's u du. So we're now in a position to find the antiderivative, which is u squared over 2 from 0 to ln of 5. And we get a quarter times ln of 5 squared over 2, which is ln of 5 squared over 8, and that's the answer. So there you have it. That's the average value of a function. So here's the recap of today. We talked about work, and we talked about average value of a function. These are both applications of the definite integral. And with that, we are done with this lecture.